Hi everybody, good to see you again. So we are going to be talking about binomial distributions today. And these are probability distributions for a very special type of probability experiment. And before I get to the actual definitions and tell you what a binomial experiment is, I want to give you several examples first, okay? And the first one is one that we're very familiar with, where we have a fair coin that is tossed 3 times, and if we let x be the number of heads, okay, we've already done that basically when we were talking about, in the previous section, when we were talking about random variables. But I just want to do this a slightly different way. Okay, so because obviously here these are all the possible outcomes that's our sample space, and because the coin is fair, they're all equally likely. But we could also notice that because each toss is independent of the others, we could just calculate this as the probabilities directly. In this case, the probability of 3 heads would be the probability of the first toss being heads times the probability of the second toss being heads times the probability of the third toss being heads. Okay, so this would be 0.5 times 0.5 times 0.5, okay, or just 0.5 cubed, okay, which is 1/8, but that's a little beside the point, okay. And you'll see though that all these other probabilities are going to be the same, right? Because in all these cases, for the probability of heads, tails, that would also be 0.5 times 0.5 times 0.5, because the probability of heads is equal to the probability of tails, right? They're both equal to 0.5, right? Okay. And the only thing that we have to note here is that the case of x equals 3 just corresponds to this outcome. The case of x equals 2 corresponds to these 3 outcomes. The incidence of x equals 1 corresponds to these 3 outcomes, and x equals 0 corresponds to this last outcome, right? All right, so what we could do here is we can see that the probability, well, let's say that x equals 3, we can see that's going to be 0.5 cubed. The probability that x equals 2, well, that would just be the probability of this event plus the probability of this event plus the probability of this event. Okay, these are all disjoint, so they're mutually exclusive, so we just add the probabilities. And since the probability of each outcome is 0.5 cubed, this would just be 3 times 0.5 cubed. Okay. Similarly, the probability that x equals 1, that would also be 3 times 0.5 cubed, because the probability of this, again, would be 0.5 times 0.5 times 0.5, added, multiplied by 3 times, right? And then the probability that x equals 0 would just be 0.5 cubed, because that's the probability of this one single event. All right, so we get that this is, we can compute, we know that this is 0.125, this is, or 1/8, this is 3/8, or 0.375, and so on. And you can see we have got a nice little symmetry here. And so we essentially have our distribution. We can actually rewrite our distribution like this, as here's 0, 1, 2, 3, and 0.125, 0.375, 0.375, and 0.125. Okay. All right, so that's the probability distribution, and we've done this before. Now, let's say if we change things a little bit and use a bias coin, where the probability of heads is 40%, or 0.4, and we toss it 3 times. Now, how can we compute the probability of 4 heads, or x number of heads? Well, first we want to note that the probability of tails, since tails is the complement of heads, and the probability of heads is 0.4, the probability of tails will be 1 minus 0.4, or 0.6. Okay. All right. So now, if we compute the probability of each of these events, probability of 3 heads, well, that would be 0.4 times 0.4 times 0.4. Okay. And when we compute that, well, that will be whatever it is. And then the probability of heads, heads, tails would be 0.4 times 0.4 times 0.6. Okay, so this will be a different. And the probability of this and this event will also be the same as this, right? It will be 0.6 times 0.4 times 0.4. This will be 0.4 times 0.6 times 0.4. But they'll be the same. You know, we're just rearranging the factors here. Okay. And then the probability of tails, tails, heads, that would be 0.6 times 0.6 times 0.4. The probability of heads, tails, tails would be 0.4 times 0.6 times 0.6. The probability of tails, heads, tails would be 0.6 times 0.4 times 0.6. And these are all cases where we have one head, and then we get 0 heads when we all have tails, and the probability of that would be 0.6 times 0.6 times 0.6. Okay. All right. So we can see that the probability of that we would have 0 heads would be this. It would just be 0.6 cubed. Probability that of x equals 1 head, that would be this number plus this number plus this number, or 3 times 0.4 times 0.6 cubed. The probability of x equals 2 would be this number plus this number plus this number. And then that would be 3 times 0.4 squared times 0.6. 0.6, and by the way, I'm sorry, this 3 should be a 2, and this is a 2, and this is 1. Okay, sorry about that. And then the probability that x equals 3, the probability of 3 heads, that's this number, so it would just be 0.4 to the third. And then we can compute this, and we get the following distribution. So here's 0, 1, 2, 3. So for 0, when we compute 0.6, let me see. Okay, so this number would be 0.216. This number would be, this number here would be 0.432. This number here would be 0.288, and this number here would be 0.4 cubed, and that would be 0.064. Okay. So that would be the probability distribution in this case. All right. So obviously now this is not a symmetric distribution like it was up here, and that of course is because we're talking about a biased coin. All right, now let's change this example a little more, and this time we are going to take the same biased coin from the previous example, and we're going to toss it 4 times, and then we can see these are all the possible outcomes. And here, this is the outcomes where we have x equals 4. These are the ones where we have x equals 3. These are the outcomes where we have x equals 2, and this x equals 1, and x equals 0. Okay. So we can see that the probability that, let's say, x equals 0 is just the probability of this event. Once again, the probability of tails is 0.6, so the probability of this would be 0.6 times 0.6 times 0.6 times 0.6, or 0.6 to the 4th. The probability x equals 1, that would be the probability of this plus this plus this plus this, and the probability of any one of these would be 0.6 times 0.6 times 0.6 times 0.4, okay, or rather 0.4 times 0.6 cubed, okay, but because there's 4 of these, we'll put a 4 in front here. And the probability of exactly 2 heads would be the probabilities of all these events, and the probability of any of these events would be 0.4 times 0.4 times 0.6 times 0.6. So this would be 0.4 squared times 0.6 squared, and there are 6 of these, so we get 6 here. And then the probability of x equals 3, that would be right here. That would be the probability, add the probability of all 4 of these events, and the probability of each of these events would be, in this case it would be 0.4 times 0.4 times 0.4 times 0.6. So this would be 0.4 cubed times 0.6, and there are going to be 4 of them here. And then finally the probability of x equals 4 is the probability of just this one event here, and that would be 0.4 to the 4th power. Okay. So computing all of this on our calculator, we get the probability distribution would look like this. Okay, and the probabilities would be 0.0256, 0.1. Oops, sorry, I'm copying this the wrong way. Well, hang on, let me just write these. It'll appear in a minute. Okay, and there it is. All right. So, there we go. All right. Let's modify this just yet one more time, and we won't do the whole distribution in this case, but for example 4, we're going to take the same biased coin from example 2, and now we're going to toss it 10 times. And let's say if we can do these, answer these questions without writing down the entire sample space, okay? Here we have, what's the probability that we have exactly 5 heads, okay? Well, one way to think about this is, we're looking for an outcome with 5 heads and 5 tails, okay? So we might have these are our 10 tosses, okay? And I say, okay, I want you to give me an example of where we have exactly 10 heads. So you basically choose 5 positions here, right? And the key word is choose. You would choose so the number of ways this can happen would be the number of ways you can choose 5 out of these 10 ways to do that. And then because there's only 2 possible outcomes, it's either heads or tails, we'll put the tails here automatically. So the number of ways we can do this, we can have a sequence here with exactly 5 heads. That would be 10 choose 5. Okay? And the probability of this event would be the probability of heads. If you remember, it's still 0.4, so this would be 0.4 to the 5th times 0.6 to the 5th. All right, because in this case, it would be 0.6 times 0.4 times 0.6 times 0.4, 0.4, 0.6, 0.4, 0.6, 0.6, 0.4, and 0.6. But in any case, no matter, in all these cases, it'll be 0.4 raised to the 5th, 0.6 raised to the 5th, to the 6th. Okay? And this turns out to be 0.201. And for the probability an x equals 6, well, I think you can kind of hopefully see the pattern here, how we would do this. You basically, once again, take 10 tosses, and how many ways can you put 6 tail heads here? Maybe something like that. Okay, so now there are 10 choose 6 ways this can happen, and because all the other outcomes are tails, probability of this would be 0.4 to the 6th power times 0.6 to the 4th power. Okay, because you have 4 t's and 6 h's. Okay, and then this turns out to be 0.111. Okay, so hopefully you can, hopefully you can kind of see what the general pattern here is going to be. And in fact, why don't we just kind of mention that right here? Actually, we mention it on the next sheet. If you asked you for what would be the probability of, let's say, 8 heads, like I think you can see it would be 10 choose 8 times 0.4 to the 8th times 0.6 squared, right? These two exponents have to add to 10, right? So in general, if we toss a coin where the probability of heads is equal to p, and it's tossed n times, then the probability of exactly x heads is going to be n choose x times p to the x times q to the n minus x. Okay, this was what we were doing before in the last few examples. Now the good news is you don't necessarily have to memorize this. You should know about this, because this is what we'll be doing this on our calculator, and we can certainly compute this on our calculator. We're going to see there's another way to a slightly quicker way to do this. But I want you to see this is where the mathematics is coming in. All right. Now, one more example here. Now, this does not involve coin tossing. In this case, we have a population of a state. In the state, 40% of voters support candidate A, and 60% support candidate B. Okay, so let's say we already know that, and we select 10 people at random. What's the probability that exactly X of them will support candidate A? All right, now I put this little thing in parentheses because to be completely at random, I know this seems silly, but we're going to allow one person to be picked more than once. Okay, so we're totally picking at random. Normally, if we were if we surveyed one person, we'd remove them from the population, and the probabilities would be ever so slightly changed. But we're going to make it completely random, so we're going to leave open the possibility that someone could be picked more than once. But let's just say that with that out of the way, let's say what are the probability that exactly X of them support candidate A? All right, well, in a way, this is kind of like a coin toss in the sense that you're going to have 10 trials, and the outcome of each trial, someone's either going to say A or B. And the probability that they say A is 40%, or 0.4, and the probability that they say B is 60%, or 0.6. So that's kind of what, in a way, is kind of the same thing. We can say an outcome might be something like this: A, B, 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 A, B, B, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this would be like an outcome. Instead of heads or tails, we have A's and B's. But we think we can see the probability of an A would be 0.4, the probability of B would be 0.6, and in this case, like in this case, we have 3 A's and 7 B's, right? So let's say this is, so if we wanted to find the probability that exactly 3 support A, how many ways can you put 3 A's in here? Well, it would be 10 choose 3 times 0.4 cubed times 0.6 6 to the 7th power, right? Because this 10 choose 5, that's again the number of outcomes where we have exactly 4 A's here, or exactly 3 A's, okay? And this is the probability of exactly one event like this. So in general, the probability of X people supporting candidate A would be 10 choose X times 0.4 to the X times 0.6 to the 10 minus X. Okay. So that is going to be hopefully you're getting to see a pattern here. Okay. And let me just give you, now let's just cut to the chase and give you the definition of a binomial experiment. So a binomial experiment is a probability experiment such that we have 4 things have to happen. The experiment has to consist of 10 independent trials, and there are only 2 possible outcomes of any trial, success and failure. And the probability of success in a single trial is P, and the probability of failure in a single trial is Q, which is 1 minus P. So the important thing is the probability of success is always the same, and the probability of failure is always the same. And then we create a random variable X, which is equal to the number of successes. And this is going to be I put success and failure in quotation marks because we don't really want to look at something as necessarily good or bad. Instead of success, we could just call it outcome 1, and instead of failure, we could call it outcome 2. Okay. The main thing is when a binomial experiment, you have to have 2 possible outcomes in a single for each trial, and the probability of the first outcome is always the same, and the probability of the second outcome is always the same, no matter what trial you're doing. Okay, the two outcomes. That's why that's the bi in binomial. Okay, so the probability distribution then, we want to find the problem that of the probability of k successes. This would be n choose k times p to the k times q to the n minus k. Or if you want to look at this way, the probability of x successes would be n choose x times p to the x times q to the n minus x. Right? All right. So, again, we can do this on our calculator. I'm going to show you a slight shortcut in the next video, but let's take a break now, let it sink in, and I'll continue in the next video.